Hello everyone, welcome to my new programming club. Today we will be solving another daily lead code challenge, and the challenge name is Unique Binary Search Trees Part 2. So the challenge statement goes like this: given an integer n, return all the structurally unique binary search trees which has exactly n nodes, and you have to construct those n nodes from values 1 to n, and you may return your answer in any order. So the binary search trees that you will be constructing, these ones, the order does not matter here. So you can return them in any order. So let's look at the constraints. What are the constraints? Constraints are pretty low. N is of the order 10, n is of the order 8. So as long as your solution does not exceed 10 raised to power 8 operations, or does not equal exceeds it, or reaches equal to it, you will not get a TLE. So constraints are not of a major worry here. So those of you who are not familiar with how the time complexity of a accepted solution varies with the input size, time complexity of accepted solution varies with input size. I will provide a link for an article describing this. Then uh, you will understand what I'm talking about here. Basically, right now what I can tell you is, in 1 second, you are allowed 10 raised to power 8 operations, and if your solutions operations exceeds or becomes equal to 10 raised to power 8, then you may get a TLE. So it should be lesser than that. And since the constraints are here pretty low, so you will not reach that complexity. And you have to also know that given for a let's say n numbers, given n numbers, and you have to construct let's say a binary tree from these n numbers, then there will be total number of Catalan nth Catalan number trees possible. Number of BST possible. Trees are binary search tree. Number of binary search tree possible. So what is a Catalan number? Catalan number is just a sequence of numbers, just like there are sequences like Fibonacci. Pardon me if the spelling is incorrect. I hope it does not affect your understanding. So this is just a sequence of numbers, and nth Catalan number is generated by this formula. 2n factorial divided by n plus 1 factorial by nth factorial. For example, let's move to the sample input. Here n was given 3. Now, if you want to find out how many binary trees will be possible, we will put n in the formula, 2 into 3 factorial, 4 factorial plus 3 factorial, and it will be 6 factorial, 4 factorial, 3 factorial. So which turns out to be 5. So I hope you are able to understand. So we know how many times at least how many times our solution should run so that all the binary trees are generated. Binary search trees are generated. So we know the time complexity. This will be the time complexity that the approach I will be discussing in the next slides. So let's quickly dive into the approach. What we will do is, uh, let's say you are given n numbers 1, 2, 3, 4, 5. And those of you who are not familiar with what a BST is, a BST is such a tree that its root node, the left part of its whatever is in the left part of the root node, it will be smaller than the root node, smaller than the root node's value. It is in the right part of the root, it will be greater than the root, greater than the node's value. All the values here will be greater, and all the values on the left side will be smaller. So if you do a in-order traversal, those of you who are not familiar with what is a in-order traversal, I will also provide a link for these two. So if you do a in-order traversal BST, you will get the sorted output. So the numbers you will be getting, the nodes, the sequence of the nodes you will be getting will be in the sorted format. So that's what a binary search tree is, and also all the subparts or the subtrees of these nodes. Let's say these are the subtrees. These will also follow the same property. These nodes will be smaller than these ones are smaller than this, and these nodes are smaller greater than this. So I hope you are able to understand what a BST is. Anyhow, you will be provided a link where you can explore further what a BST is and what in-order traversal of BST is. So, how will we be constructing the binary search tree? What we will do is, for the root of the binary search tree, we will be having n options. In these n options, we can pick any one of them. Let's say I pick fourth number. I pick this number. And so what will happen is, since I mentioned that if you do the in-order traversal, you will get all things in sorted order. So since these are the numbers smaller than the root, and binary search tree, the left tree is smaller. So left subtree is smaller. So what you will do is, it will be the root, and these values will be in the left subtree, and these values are since greater than the current root that we have considered it as root as of now, and you are having n options to consider root. So these options from 5 to n will be in right subtree. So this will be a uh, binary search tree possible. There are other binary search trees possible also. For example, if you take 3 as root, then you will be having 1 to 2 in the left subtree, and from 4 to n in the right subtree. So these are the options that you will be accessing. Now if I somehow give you, and we will be doing so in a recursive way. Let's say now somehow I give you, uh, let's talk about this left part first. Left part will be 1, 2, 3. So you will again be having 3 options to consider root for this subtree, and depending upon which options you consider, you will be having 3 different uh, trees in the this generated from this particular subtree. Subtrees will be generated. Let's say T1, T2, T3, and this, let's call this left part. Similarly, for the right part also, uh, you are having choice 5 to n. So let's call this right part. Similarly, subtrees depending upon the which choice you make for the current route. You will be getting trees T1, T2, T3 and so on. So if I give you these two lists of uh, different subtrees routes depending upon your choice, what choices you will make, and you are having the current choice that you have made F4, and you are having left part here as the list is having the routes possible for left subtrees. And similarly, whenever you will be making a subtree, you will be then again following this logic. According to your choice available, the routes will be generated and a list will be available. So this consider this as a recursive function. You are generating two lists. One is of left part, one is of right part, and the list is having the possible routes for that subtree. Now let's say how will you be generating the whole trees. What you will do is you fix root and the right subtree or left subtree depending upon your choice. Now here I am fixing two things. I am fixing the root and the right subtree. Okay, and then if I fix this, I will be iterating over the left part. Now based upon the what value I have fixed here, uh, each value, each possible root in the left part, T1, T2, T3 and so on, will generate a different tree. So I hope you are able to understand. So you can also fix the left part and iterate over the right. You can also fix the left subtree. Let's fix it and fix this also. Let me quickly change the color so that you won't be getting confused. Uh, let's say right now this is not fixed. What you will do is for these two fixed things, for each value in the left part, you will be making combinations with the right part. So I hope it's clear, and it will generate different subtrees. And you will be doing this thing in a recursive manner, so that each subtree, different combinations will keep on generating. And at last, when the recursion will, what will the recursion return? Recursion will return you all the subtrees generated. And you won't be doing extra work in making same choices again and again, because you are storing the calculated roots of subtrees in left part and right part. These are nothing but the lists that are carrying the possible number of roots based upon your choices, which will be available in the left subtree and the right part. Okay. Now what we will be the time complexity of the solution. It will be number of binary such tree possible into work done for constructing them, which is nothing but uh, number of binary search trees possible for with n values, from 1 to n will be nth Catalan number into work done. What will be the work done? It will be nothing but n are the number of values or number of in BST. So it will be our time complexity. And since the what will be the space complexity here? Hmm, what will the space complexity? It will be nothing but space used for storing subtrees, left part plus right part plus space used for recursion stack. Recursion stack space. So this will be your space complexity. Now let's quickly dive into the coding part of the problem. There you will be able to understand the solution in a much clearer way. Now let me quickly zoom out so that you will be able to see more of the codes part. Yeah. What we have done is we have taken range of numbers from 1 to n for the range of numbers 1 to n. We are considering the choices for the root of binary such trees, such tree possible. So initially you will be having 1 to n choices, which will be nothing but let's call uh, one here is start and n as end. What you will be doing, you will be doing this whole thing recursively that I have just explained you here. This thing you will be selecting any one choice for the root, and depending upon the root rest will be included in the left part and the right part. So what we have done is if the start is happens to be greater than the end, you will add null to it. It may happen that, for example, if let's say 1 is the current selection of the root and you were having initially these many choices only, then you will consider its left part. Now left part you are having nothing, so your left part will be of there is nothing here, and for the right part also there is uh, no option available. So in these cases start will be greater than the end and you will be returning null, or you will be adding null to the lists. I hope you are able to understand. This list is containing nothing but the possible of the current subtree. So currently you are having start choices from currently for the root of current subtree. You are having choices from start to end. So depending upon your choice, you will be adding those roots here. This list will contain possible roots of the current subtree. So it happens if you reach a null node Then you will add null value list. And what will be the type of list? It will be user defined data type. It will be tree node, since we are storing root values of addresses of the nodes. So what you will be doing is you will be checking for the possible roots of current subtree, and then you will be forming its left part and right part. These are nothing but the right part of the current choice of the root for current subtree. And similarly, this is also the left part of the current choice of the root for current subtree. I hope you are able to understand it. Then what we will be doing is we will fix root plus either left part or the right part, root plus either one of them, and making combination with the part that is not fixed. So here we have fixed the right part of the current subtree, its root and its root. And we are making combinations with the part which is not fixed, which is the left part. So according to the combinations made, you will be adding that node in the node to the as the left part and right part of the current according to the, let me type it, according to the combination found, you will attach the right and left parts to the current root of the subtree, and you will be adding that root to the list which is having possible roots of current subtree. So this will form a one possible configuration for the root of current subtree, and at last recursion will return you all the binary search trees possible. And time complexity and space complexity we have discussed. So this is pretty much it. This wraps up the solution for the problem. Now if you are having any doubts, feel free to ask your doubts in the comment section. Thank you for watching. Thank you.